So in this video we're going to continue our discussion of the frequency domain and thinking about signal structure in the frequency domain in addition to the time domain. We're first going to prove something called Parsifal's theorem, which shows us how to compute the power in a signal entirely in the frequency domain. In many cases it's easier to compute it that way than directly in the time domain. We'll then talk about constructing signals explicitly in the frequency domain. That's a digital communication example. It's a lot of fun to see a little bit, get a little glimpse of what digital communication is all about. And finally, we're going to filter a periodic signal. It's a fairly simple extension of what we've already done when we talked about analog filters. All right, so the crucial thing we're going to prove is something called Parsifal's theorem. And this is a very important result in the consideration of signals and their power. So just to review, this is the Fourier series of a periodic signal S. It's got a period of capital T, and we know these are the Fourier coefficients, and it's expressed as a superposition of complex exponential signals whose frequencies are harmonics of 1 over t. To find the Fourier coefficient, we calculate this integral. We have to plug in what the signal is and just do the integral and find it for all k. Okay, so here's Parsifal's theorem stated in words. That power in the time domain equals power calculated in the frequency domain. So let's see what that means. First of all, the power in a signal is given by this expression. Now, we've talked about power in terms of circuits, voltage and current. And the idea here is that the average power of a periodic signal is going to be related to the integral of the square of the signal as if it were being passed through a 1 ohm resistor. So that's the idea. So if you look back at the power formulas, no matter if this is a voltage or a current, this would be the average power expression, assuming it was going through a 1 ohm resistor. I want to really point out that this is a very general expression, but the power over here is not in watts. It's proportional to the power expressed in watts. Of course, it depends if it's a voltage or current and what the value of the resistor is it goes through as to whether this expression is numerically correct. It usually isn't, but for theory, we'll figure that out later. But this is the key element. The power in the signal, of course, depends on the signal waveform, how big it is, all kinds of things. So, how are we going to prove Parsifal's theorem? And the idea is that I'm going to take this expression for the S as a Fourier series and plug it into there. And I want to do a little bit of mathematics because we have the square of a sum. So let's talk about, just in general, suppose I have a sum, AKs, and I square them. What's the expression for that? Well, it's not the sum of AK squared. That's not the answer. It's a double sum, which I'm going to write as a sum over K and L of A sub K, A sub L. And to see that, look at the very simple example of x plus y squared. Well, that's equal to x times x plus x times y is equal to all possible pairwise products. Right? So that's why this is equal to that. And so when I plug the Fourier series into this expression, I'm going to make use of this property here. Okay. So, what is 1 over t, the integral from 0 to t, of the double sum, k and l, of c sub k, c sub l, e to the plus, and I'm going to combine the exponential parts, and this ought to look very familiar from the previous video, because this has to do with the orthogonality relationship I showed previously. What I'm going to do is push the integral inside so it becomes clear. And now we know what the value of this integral is. This integral is equal to 0 if k does not equal minus L. Remember that situation when we got 1 occurred when this term right here was 0. So the integral is 0 when k does not equal minus L. It's equal to 1 when k equals L. Well, that's great. So this becomes equal to, and by the way, when the 1 over t makes this a 1 up here, so we have the sum over k of c sub k, c sub minus k. Well, remember our properties? What is c of minus k? That's equal to c k conjugate. Conjugate symmetry here. So, c sub k times c sub k conjugate, that's the magnitude squared of c sub k. So that's Parseval's theorem, is that the power of a signal can be expressed, can be calculated, expressed either in the time domain or in the frequency domain. The expressions are very similar in that you square something and add them up. Integration is like adding in many ways. So this is quite useful. You may decide that this is an easier way to calculate power than this, and I'm about to give you some examples of when that's true. And that comes up when you think about using the Fourier series as an approximation when you have a finite number of terms. So for all kinds of reasons, you may decide I only want capital K terms in my Fourier series. Going from minus k to plus k is what I mean by capital K terms, rather than the full series. Well, how good is that approximation? Well, we can talk about the error, which is this, the original signal minus the approximation. Well, when you subtract out essentially the middle terms out of this sum, what you get left are the terms from minus infinity to minus k minus 1 and from k plus 1 to infinity. Well, you think about this another way, this is just this, these terms over here are just the Fourier series for the error signal here. So how much power is in the error? The RMS value, square root of power, it's given by this expression. So I did a few things here to point out something. We know that for negative frequency, negative index, that c sub minus k is equal to ck conjugate. That means the magnitude of c of minus k squared is equal to the magnitude of c sub k squared. So when I sum up, as Parseval's theorem says, from minus infinity to infinity, the negative index terms, negative frequency terms, are going to be the same as the positive frequency terms. So you can write the whole thing, and this is a very good example of why you want to do that, is only being over the positive index parts, and you put in a 2, because you get, that's including the negative frequency terms. Okay, so now we have an idea of how well the Fourier series with k terms approximates some signal. We can look at the RMS value of the error signal. Great example of using the frequency domain to calculate power. So go back to our approximation of a square wave. Here we have a plot of the magnitude squared of k, and you can see it decreases like 1 over k squared, like we would expect. Notice the square. And now if you look at the RMS error that's calculated from the expression given above, you see it's going down, but it doesn't go down very quickly. That's just, so this tells you that if you want to approximate the Fourier, want to approximate a square wave with a Fourier series, you're going to need lots and lots of terms. 49 is a pretty high number, And that gets the error down to around about there. I calculated it earlier. So if you really wanted something with a very, very small error, you're going to need lots of terms in the Fourier series. It's a very interesting way of looking at it, I think. So there's an alternate view of using the Fourier series to approximate a signal, and that is to measure its distortion. So the idea is I have some periodic waveform. In this example, it's just the square wave. And the question is, how close to a sinusoid is it? And this is called harmonic distortion because this is used in audio to assess how linear amplifiers really are. And the measure that's used is called the total harmonic distortion, very long term. So THD stands for total harmonic distortion. And it has the following definition. The numerator is the power in the higher harmonics. Notice it starts at 2, and of course this 2 has to do with the fact we're including the negative frequency terms as well. And the denominator is the power in the signal. Now, the little detail here is that you subtract off C0. And the reason for that is that C0 is known as the average value of the signal. Right? If you look at the formula for computing C0, you'll see it's just the integral of the signal over a period divided by the period. Well, that's called the average value. In computing harmonic distortion, I'm interested in how it departs from a sine wave. I'm not really interested in whether there's a average value that isn't 0, if it's shifted up or down. That's really not the issue. The issue is how much does it depart from a sine wave. So that's why this little term in here, it's kind of a detail, and certainly for my square wave example, C0 is 0. But you'll notice the numerator ignores C0 as well, and so using our Fourier series expressions through Parsifal's theorem, we see that the power in the signal, forgetting about the average value, is that, and the numerator is that. Well, to compute the harmonic distortion, I would have to plug in what the Fourier series is and do this sum. And got to tell you, that's really not a terribly good way of doing it, because those sums, by and large, do not have closed form expressions. So let me point out something, that this is equal to the power in the original signal, which is all the terms summed up from 1 to infinity, that's the denominator, minus the power in C1. The first harmonic is what that's supposed to mean. So I can use that to compute my numerator. The only thing we have left is to compute the power in the signal. Well, that's easily done. You just square the signal, which in the case of the square wave is going to give us a value of 1. Integrate that over a period, divide by the length of the period, we get 1. So we can find the power in the original signal usually quite easily. So C1, if you remember what the Fourier series is for a square wave, is just 2 over j pi, which makes that numerator equal to 1 minus 2 times 2 over pi squared. And this 1 is the power in the signal, which we calculated just by looking at what the waveform was and acting accordingly. Well, you plug in the numbers, you do the calculations, you wind up with about 20% harmonic distortion. What that means is that the square wave has about 20% of its power in higher harmonics, and another way of saying it is that the sine wave approximates the square wave in such a way that it captures 80% of the power. Well, it turns out that's a spectacularly large harmonic distortion. The idea is, in audio, is that you want to assess how linear an amplifier is. If the amplifier were perfectly linear, if you put in a sine wave into your amplifier, you put in a sine wave, you should get out a sine wave, a perfect sine wave, which would make the harmonic distortion 0 because all of these are 0. Well, amplifiers have some moderate amount of distortion, and so you want one number that quantifies how linear it is, and they use total harmonic distortion for that through a series of test equipment. Harmonic distortion of even 1% is considered pretty large. In fact, all audio amplifiers are specified through their harmonic distortion. Let's explore the frequency domain in another case of digital communications. I want to tell you how digital communication works. We're going to explore this in much more detail later. So here's the idea. I want to send a bit, either a 0 or 1, to the sink, to the receiver. And one way of doing it is either to send nothing over an interval of length t to represent a 0, or you send a sine wave to represent a 1. And to send a sequence of bits, you alternate between a 0 and a sine wave depending on what the bit is you want to send at any one time. Okay. This is a 1 bit at a time scheme. So I'm sending 1 bit within the interval 0 to t. Well, you can think of a fancier scheme which sends 2 bits at a time. So instead of just thinking in the same t-second interval, I can, to send 2 bits, 0, 0, I'll just send nothing. If I send 0, 1, I'll send a 0 plus a sine wave at a given frequency. But if I want to send 1, 0, I send a sine wave of a different frequency. And finally, if I have both bits are 1, I'll send the sum. Essentially what I'm doing is constructing the transmitted signal in the frequency domain by essentially using superposition and indicating which are the 2 bits are by choosing which frequencies are turned on and turned off. So that is a total construction of a signal in the frequency domain. Here's an example where I've got, here's the frequency F1 is over here, and the frequency F2 is over there. And here I have the sequence 1, 0. Here's the sequence 1, 1. Here's the bit sequence 0, 1. And here's the waveforms that are produced, entirely constructed by thinking about encoding information, encoding bits as in the frequency domain by representing them by frequencies. So again, you want to think about signals both in the time domain or in the frequency domain, depending on what the application is. Very useful to be flexible and be able to go back and forth depending on what the application is. Okay, now we need to filter a signal. So we know how this works from what we've done with circuits. We know that if the signal is a complex exponential and the filter is linear in time invariant, that the output is given by the transfer function times the complex exponential of the same frequency as the input. So given the transfer function, we know what the filter is going to do. And of course, if the frequency is just harmonic of some 1 over t, we just plug into the transfer function what that frequency is, and of course we carry along the frequency of the input. And as I showed you when we talked about circuits, if you have a superposition of 2 complex exponentials, the output is a superposition. This is the definition of a linear system. So guess what happens when you have a Fourier series? It's just a superposition of lots and lots of complex exponentials. So the output is given by the transfer, sum of the transfer functions evaluated at those harmonic frequencies times the C sub k's for the original signal. So in essence, this is the Fourier coefficient for the output. So what do? To figure out what a filter does to a signal, you start with the signal, usually in the time domain. You find its Fourier series representation. You find those C sub k's. You plug that into this expression along with the transfer function, evaluate at those harmonic frequencies, and reconstruct what y is. So start in the time domain, go into the frequency domain, figure out what's going on there, and then reconstruct in the time domain. This may seem tedious, but it turns out to really be a easy way of doing things and very efficient, as we'll see a little bit later. Okay, so let's do an example. So here's a filter, and the input I'm going to use is a periodic pulse train, and we know what that spectrum is. I'm not going to write the expression again, it's pretty long-winded, but of course it has a Fourier series. And the filter I'm going to put it through is our old friend, the low-pass filter. So if you recall, the transfer function is given by that expression. And if you were to plot the magnitude as a function of frequency, it rolls off. And it has a cutoff frequency, which in this case is equal to 1 over 2 pi RC. We showed this in previous videos. Well, I want to figure out what happens when I put this periodic pulse train as the source signal, so that's going to be x of t. The output, V out, that's going to be y of t. So how do I find it? I use the superposition principle, and this is what we get. Here's the transfer function, and here it is evaluated at k over t, the kth harmonic. Multiply it times c, and then reconstruct the signal. Well, this reconstruction, to say the least, we can't do it analytically, and so this is where you just call upon a computer that can evaluate these things and add them up. And here's what you get. Really kind of interesting. So, first of all, I had to tell you, or I had to pick what t was, the period of our periodic pulse train. I picked 1 millisecond. What does that make the fundamental frequency, the first harmonic of that signal? What is that frequency? And of course the answer is it's 1 over t, so it's 1 kilohertz. Let's keep that in mind. And along with the previous example that I gave for the periodic pulse train, the width of the pulse is about 20% of the period, okay, which corresponds to the examples I showed. So I'm now looking at what happens to the output. The outputs are shown down here. This is the spectrum of the output. So these are the Fourier coefficients for filters of various cutoff frequencies. So I'm changing R times C to produce these various cutoff frequencies. Okay. Don't forget that the fundamental is at 1 kilohertz. So if you recall, the Fourier series for a periodic pulse train has power at all harmonics of the fundamental. So it has power at 1 kilohertz, 2 kilohertz, 3 kilohertz, 4 kilohertz, etc. Okay, so picking a cutoff frequency of 100 hertz, that's really low-pass filtering. The first harmonic is well above 10 times the cutoff frequency of the filter, so it attenuates the spectrum of the input a lot, as you can see by this figure. And you get produced a somewhat lumpy looking output. It's not even clear that there were pulses in there originally. It's really low-pass filtered. So low-pass filtering tends to produce signals that don't vary very much in time. They can't wiggle very quickly because the higher frequencies have been suppressed by the filter. They're low-pass, remember. They tend to attenuate high frequencies. When the cutoff frequency is now 1 kilohertz, which is right at the first harmonic won't be suppressed very much, be suppressed by 1 over the square root of 2. You can sort of see the pulses coming out, kind of. It's not clear the original were pulses. You tend to get what I call the shark fins. So it goes up and it comes down. It goes up and comes down because it's periodic. The output is periodic, of course. And then when the cutoff frequency of the filter is well above the first harmonic, well above the 8th harmonic, 9th harmonic, it's way up there, what you see is that the output very closely resembles the original pulse. There you can see, if you look very carefully, of course, you can see it, that it's rounded edges here, both at the tops and at the bottoms. So it doesn't filter very much, but if it's the cutoff frequency is really low compared to the first harmonic, you get a lot of change of the output. And this is a common use for low-pass filters, is to change the waveform to be something that you want, given some very simple waveform that you could probably produce in the lab. Okay. So, signals can be defined either in time or frequency. What I concentrated on in this video are frequency domain characterizations of signals. So the idea was I started with C sub k's and I used that to construct signals. And going the other way, you can take your signal, of course, and figure out what its frequency domain representation is. And that really means you can go either way. You can start in time, go to frequency, start in frequency domain, go to time. All choices are available to you. So you can define them in either domain depending on the application. You can also study the structure of the signal in either domain. You may be very interested in what the pulse width is, for example, but you also may be interested in how high up, what's the highest harmonic that's needed to have a 90% approximation of the original pulse train. Either way of thinking about it may be important depending on the application. And finally, for linear time invariant filters, we can determine their outputs for periodic inputs because we can use the Fourier series results that we've gotten in superposition to get the answer. So we're really becoming more sophisticated. Next video, what we're going to do is drop periodic. We're going to talk about how to generalize these results so we can talk in general about general signals. They don't have to be periodic or not. And that means we really know a lot about signals and systems.